All right, today we're going to talk about rotational equilibrium, but before we do, we're going to go back and just review translational equilibrium. Now, when we talked about the first time, we just said equilibrium, but it's translational because it's moving in a nice straight line. When something is in translational equilibrium, the forces balance. Okay? Recall back to when we were in our previous section about forces, and we would talk about the net force was equal to 0. Okay, that's what this means. The net force equals 0. And we use that in a lot of problems. We decided the object wasn't moving, so we knew the net force on it was 0. So the up force is balanced with the down forces, and the left force is balanced with the right forces. Okay, but it doesn't mean it's definitely not moving. If the net force is 0, it simply means there is no acceleration. Which means that it's either not moving, which is the one I just reviewed, or it's moving, but moving at a constant velocity. Okay, if you recall back, we did a lot of problems where in the problem it said it was moving at a constant velocity and we had to find a coefficient of friction and things like that. And we used the fact that it was a constant velocity to tell us that the net force was equal to 0, and we got our equations from that. This is very similar when we take it over and talk about rotational equilibrium. Okay? But in rotational equilibrium, it's not the forces that balance, it's the torques that balance. Okay, so that means that the net torque on the object is equal to 0. That means there is no angular acceleration. Okay, it could still be changing direction, but it is not going to be speeding up or slowing down. Okay, alpha is going to be equal to 0. What does that mean? Well, that could mean it's not moving. Okay, it's not moving, then it's not rotating. It's not doesn't have an acceleration. Okay, it's not speeding up or slowing down. Okay, or it could be moving, but at a constant angular velocity. So omega is going to be the same.